Okay, next type of application, find and classify stationary points. Now we know about this. To get a stationary point, we need to differentiate and solve when the derivative equals 0. So we're back up to this, and we'll be saying f dashed of x. It's just simple functions there. So the derivative of x is 1. The derivative of e to the minus x, we write e to the minus x, but then we times by the derivative of what's upstairs, which is -1, so we get minus over there. We would like to solve when that equals 0, so 0 equals 1 minus e to the minus x. I will now put the minus on the other side, so e to the minus x equals 1. How do I get rid of e? I ln, which leaves me with minus x equals ln1, and we know that ln1 is 0, so at x equals 0 we've got a stationary point. Now we want to classify it, so that means you have to draw a sign diagram. You can't just leave it as that. So we go 0, we pick a value this side of 0 and substitute it into the derivative. So if we go 10, remember e to the anything is going to be positive, but we'll use our calculator, just doing that off screen. So e1 minus e to the minus 10.999, but that is still positive. Then we choose less than, so minus 10, 1 minus e to the minus 10, so to the 10, and e to the positive 10 is in a massive number, so we get minus. Therefore, we've got a local minimum at 0, so you must write that down, local minimum at 0, and to get our y value, we substitute that back into here, so 0 and e to the 0, anything to the power of 0 is 1, so it's 0, 1, we know a minimum exists. Okay, discuss f of x as x tends to infinity. Well, we love these questions. Okay, B, discuss f of x as x tends to negative infinity. I know you love these questions. So in order to do that, it's really important that you understand what this graph looks like. So you could use your graphic calculators or the sheet that I gave you, but we know this is what this looks like. So as x is getting more negative, that's what that means, tending to infinity, as it's getting more negative, what's happening to the y values here? The y values just keep going up and up and up and up and up, so it's increasing, it's going to a bigger value. Now, you might be thinking, well, hang on, this x, as x is going more negative, this is getting negative too, but remember this is an exponential function, so when this is maybe minus 100, this becomes e to the minus minus, so positive 100, which is a massive number, which far outweighs the minus 100 there. So we will just say that as x tends to negative infinity, f of x approaches or tends to infinity, which means it's just getting bigger and bigger and bigger. Onward and upward. So C, just when you thought you were out of the woods with the approaching infinity, explain why the graph y equals f of x becomes more linear as x gets large. So again, that is asking you to consider as x approaches, this time positive infinity. So let's have a look again at this graph here. As x is getting more and more positive here, larger positive, the y value is getting closer and closer to 0. So we could say here that as x is approaching infinity, e to the minus x is approaching 0. Therefore, as x is approaching infinity, f of x is approaching, so this part of the graph is approaching 0, so that's disappearing, which means we're left with x. So that means f of x is approaching x, which is linear, and that's all that's required. Okay, let's hit D. We want to find the second derivative, determine its sign. So derivative of 1 is nothing. E to the minus x, we write that. There is a minus here, but then we have to times by the derivative of -1, which is negative, so we get that. what's it on about with its sign for all x? Well, again, if we look at this function e to the minus x, it's always above the x-axis, which means it's always greater than 0 for all values of x, for any value of x. Okay, we now want to sketch the graph. Well, you can probably type that into your graphics calculator and have a look at that. One that we prepared earlier over here. Oops, can we move that? No, I can't. Okay, well, managed to move that. It's not great, but I've just typed in the function. We can't see that. And I set it to standard view, and we've got that. Now we expect here that our minimum, so gsolve, is that the minimum there? Yep, is 0, 1. You can't see, but there's a 0 just outside of the screen. You should do this on your calculator. So that's pretty much, it agrees with what we had, where it said that we had a minimum here of 0, 1. So it's pretty much on the right track. We're also saying that as x is getting bigger and bigger and bigger, it was becoming more linear. It was approaching, in fact, y equals x. And so that looks like that is indeed the case. That line there, I think, is pretty much y equals x. So fits in with all the information that we've had here, and it's really important that you do check that. Alright, and now when we've got deduce that e to the minus x is greater than or equal to 1 take x, you go, well, how on earth are we meant to do that? Well, if you go back and look at your original function here, that's that one. Okay, so here's our graph that we've drawn really quickly. Now deduce this expression here. Well, because you've proved that this is the minimum, this y value is your minimum value, which would mean that every other point is greater than that. So we could say that therefore as 0, 1 is the local minimum of f of x, then f of x is greater than or equal to 1. In other words, x plus e to the minus x is greater than or equal to 1. And if we now rearrange this, so I'm going to get rid of this plus x and take it over the other side, we get e to the x is greater than or equal to 1 minus x, which is what we wanted. I've put all of this stuff in here because they gave us this, and it's really not explaining it a lot if you just have this and then this line. So put a little bit of explanation so you make sure that you get your maximum marks. And that's it for a typical graphing question. I mean, it could be, instead of e, it could be ln, it could be using the product rule. Just practice your skills of your differentiation and solving. I hope this helps.